Hello and welcome back to the episode 6 of the Calculus 1. I am Mohammad Momenzadeh, the presenter of this lecture. So in this lecture we will discuss about the continuous function, the main key of topological properties. We try to express the continuous function in the easiest and simplest way that we can describe them. However, if you're interested in that topic, you can follow the topic of the continuous function in a topology or real analysis lectures. So this is the main key of the topological properties because it's preserved the topological properties when we want to transfer some shape or some type of the graph from one space to the another space. The topological space topological property will preserve with that type of the function. For this reason, this is the main key of the topological spaces. So we are not going deeply in that type of the topics. I know that you will have some difficulty for understanding that type of the things without having a good background in the topological properties or that concept. But we try to express this type of the function in the easiest way that we can have it. So we will discuss about the different type of the discontinuity as well, and we have some examples, and if we have a time we will go to the definition of a derivative as well. So let us take a look at the continuous function and see that how we can describe the continuous function. So as you can see, we have a two-dimensional space, and normally when we have a two-dimensional space and if we have a single variable function and determine the y lines or the y-axis as the output and the x-line as the input or the horizontal line as the input, then we can sketch the graph of a function. So when we discuss about the continuous function, means that if we want to sketch the graph of a function like this, then without removing the pen from the space from the page, we can sketch the graph of a function. For instance, over here at this point I have a gap over here, and it's happened because I moved my pen from that point. So we should find a way to describe this situation by describing the situation by using some mathematical concepts. So the concept that we needed over here is a limit indeed. At this point that we have a gap, as you can see, if I name the point as a, then you can see that the right side limit and left side limit are not the same, so the limit does not exist at that point. If we approach to the point A from a right side, then you can see that the value of a limit can be calculated as a value that we have it at the top. And as you can see, I just try to reach to the point A from a right side, and the value, the corresponding value for the right side limit is given over here by L, for example. And if I just reach to the point A from left side, if I approach it to the point A from left side, then the limit will be different, and it can be described over here. It can be named by the point M, and M and L are not the same, so the limit does not exist. And as you can see, there is some discontinuity at the point A. Normally we define the continuity at one point, then by expanding this concept to all points of one interval, we can discuss about the continuity in an interval. So at the given point A, we can define the continuity as following. However, there are a lot of definition for the continuous function, and it can be more general, but we are not looking for the sake of having the general definition. We are looking for some applicable definition over here. For calculus, we have this definition. As I said it, we have more general general and better definition, but it's suitable for the topological course or some real analysis courses. So over here, as you can see, to have a continuous function, the first thing that we need is having a limit. So at the beginning, for a given point, we should have a limit. Means that at the point A, the function is continuous if the limit of fx, where x tending to a is defined and is equal to some value. Means that at the point x tending to a, we should have a limit, and this limit should be equal to some value. For example, it's equal to the value of n. The another thing that we needed is having the value at that given point. For example, let us take a look at the another point of this function that we have it over here. Let me just make a gap over here and give a point like this. So if I name this point as a b, then as you can see over here, at the point b, the limit does exist, and of course the limit of that function at the point b is equal to n. However, the function is not continuous. It's like a gap or one open circle at the point b. So the second thing that we needed is having the value at the point that we talk about it. So f of a, or the value of the function, should exist at that point. This is the second thing. So but that value can be defined at the another point. For example, it can be defined at this point. Still we have discontinuity. So to have a continuous function, we should have a limit, we should have a value of a function, and the another thing is about having the equality between this value and the limit. Means that we can recap all these three conditions in one page as follow. So as you can see over here, we have a refined definition of continuity. Using the limit concept, we can revisit the definition of continuity as following. A single value function gx is continuous at point x equal to a if and only if that this three condition holds true. The function is defined at the point x equal to a, and the limit exists at that point, and the limit and the given value of a function at that point are as the same. So these three conditions should satisfy to say that the given function has the continuous value at that given point. As you can see at the right side, we have a graph of a function. At the point a, this function is discontinuous because all these three conditions are not satisfied at the point a. The right side limit and left side limit at the point a are not equal, so the limit does not exist. At the point a, the function has no value, and also the value which does not exist over here is not equal to the limit as well. So at the point b, that the function tends to infinity, indeed the limit does not exist, and so consequently the function is discontinuous. And at the point c, however, that we have a limit, means that at the right side and left side of the point c, if you are approaching to that point, the limit does exist and it's equal to this value. If I can sketch it, as a straight line, let me just use that line to determine the limit of that function at the given point. So this is the point. So you can see that over here the limit does exist and it's equal to L. But the value of the function is not defined. There is no value for a function at the point C. So because of that, we have a discontinuous cases over here. So as you can see, this is the definition for the given continuous function at that point. So let us solve some example to see that what type of the function are continuous and what type of the function are not. So as you can see over here, we have three examples and all of them related to the function sine x over x. Previously we discussed about this function and we calculate the limit of this function at the point 0 and at the point infinity as well. So over here at the first function we have f of x equal to sine x over x. We want to discuss about the continuity of this function at the point 0. This is the graph of this function, and as you can see at the point 0 the value of a function is undefined because the denominator of this function is equal to 0, means that f of 0 does not exist. You cannot calculate f of 0 because f of 0 is equal to sine of 0 over 0 or 0 over 0, and this value is undefined. It's not a limit, it's a exact value of 0 over 0. The 0 over 0 is undefined, so there is no value for the f at the point 0, so the function f of x at the point 0 is undefined, so the f of x at the point 0 is discontinuous, it's not continuous. So the second function that we have it over here as gx is defined as sine of x over x for a value that x is not equal to 0, and for x equal to 0 that value is equal to 1. This function is continuous. Why it's continuous at the point 0? It's continuous in whole space indeed. So why it's continuous? Because when you calculate the limit of this function at the point 0, means that if you calculate the limit of g of x or limit of that function, so you should calculate limit of sine of x over x. The important things about the limit is the neighbors, not in that exact value. So when we want to calculate the limit of g of x when x tending to 0, we should put the value of sine of x over x. And as you remember from the squeeze theorem, that the limit was equal to 1, and the limit and the value of a function are the same, means that g of 1 also g of 0 as well is equal to 1. So the value of a function is equal to the limit of a function, so it means that the function is continuous. So the only case that we have it over here is g of 1, which is continuous. What about the point h? About the function h over here, as you can see, again we have the same function for x is not equal to 0, but at x equal to 0 we have 42, means that at this point the value of a function is too greater than the limit. I mean, somehow it's at the point 42. So it's too much far away from the limit, which is equal to 1, and because of that the function hx is not actually equal continuous at the point 0, and as you can see h of 0 is equal to 42. So the only function that is continuous out of these three cases is the second one, and remains has a gap and has discontinuity. So it's important to have some theorem to help us to generate some type of the continuous function. For instance, some theorem that verify that all the polynomials are continuous as well. So as you can see over here, we have some useful theorem about the continuous function, and the following determine that type of the theorem as well. As you can see, we have several theorem, but roughly speaking we can say this word that up to the time that you can calculate and evaluate the value of a function at some point, that function is continuous. For example, if I have a type of a function like 4x squared minus 3x cubed plus 1, this is a type of the polynomials. So if you have a polynomials like this, 3x cubed plus 1, and if I name this function by fx, then this function is continuous everywhere. By the another word, if we have any type of the polynomials, these polynomials are continuous, and even if I divide it by the another polynomial, it continues up to the time that the denominator is not equal to 0. For example, if I divide it by x squared plus 1, then this function also is continuous everywhere, because as you know, this x squared plus 1 will never be equal to 0 in a real value. So if you have a real value for the x, then x squared plus 1 will never equal to 0. So this function will be continuous. This helps us to determine the continuous function, and the most familiar form of the continuous function are the polynomials. So we can use this type of the concept to determine one of the basic points of a numerical analysis as well. So what is that one? It's about the intermediate value theorem. Let us state the theorem and talk about that one as well. So this is the IVT, or intermediate value theorem. As you can see over here, we have this type of the theorem, and it can be helpful with that small knowledge of the continuous function that we have it up to now. We can state that powerful theorem. The theorem said that if a function f is continuous in a closed interval, for example, that interval is given by a and b, and I just take two values for f of a and f of b over here. Based on that two value, we can describe that theorem. So if I just denote the value of f of a and f of b at these 2 points, let us consider the f of a at this point and f of b at the given point at the right side. So this is the f of b as well. If the function is continuous, then all the value between f of a and f of b should be covered by the function. This is the concept of the IVT. So by the another word means that right now, if I have this value as f of a, I can denote it over here as f of a, and this value by f of b that you can see over here. Then if I choose any value between f of a and f of b, for example, I choose this value like k, then there exists some value of f between this a and b, such that it can be taken, and the value of a function at that point will be equal to k. Means that if I sketch any type of the continuous function and I started from f of a to reach to f of b, I should pass the point k. However, I just change that one severally. At the end of the day, I should pass from the point k. So let me just determine the point k over here. This is the point k that I denoted over here. I choose it between f of a and f of b. This is the point k, and if I sketch any type of the continuous function and connect the point f of a to f of b with any type of the continuous function, at the end of the day I should pass it from the point k. At this point you can see that the value of a function is given. So this intermediate value theorem is totally helpful in a calculation of a zero of a function or roots of a function. One of important things in the calculation of engineering engineering issues, is calculating the roots of a function or zero of function. Means that whenever the f of x is equal to 0. So it's important to know that for which value that function is equal to 0. In engineering we need that type of the thing too much. Means that it's important to know that where the value of a function is equal to 0. So we are looking for the value of x. By knowing this type of the things, we can evaluate the roots of a function, the zero of a function easily. Let us take a look at some polynomial and see that how it can be helpful for that cases as well. So we return to the Desmos program to see that how it can be helpful. For instance, over here I just put some, first of all let us put some quadratic equation which is too easy to determine the roots of that type of the polynomials indeed. So as you can see, we have two roots, and by using the delta formula you can calculate it. When the formula is changed to higher degree, means that if I add the x cubed to that things, then still we can use some delta formula. But if I just increase the degree to 4 or 5, then we don't have any type of the exact delta formula for that cases. So the Galois theorem said that for higher than 3 degree, we cannot determine a delta formula for that type of the functions. Let me just make it more complicated to see how we can change it and put 6, for example, over here and 5 here for this, and change the degree a bit and make it more interesting. So if I just have this form of a function, for instance, over here you can see the roots of that function at the point 0.697. However, previously we didn't have that type of the calculators to determine the roots that easy. But right now, if we want to evaluate or approximate the roots, we can use this technique. I just choose one interval, for instance the interval between 0 and 1. Let me just mention the interval of 0 and 1, and right now we have the interval of 0 and 1. Let me just put a equal to 0 and b equal to 1 and use them as a point over there, and write it as a and 0 and label that one, and b and 0 as well, and label that one as well. So right now we have this 2 points over here, so both of them are 0 and 0. It should be 0 and 0. So right now we can label these 2 points and start it with that 2 values. So I can apply the intermediate value theorem for an interval 0 and 1. Let me just describe it over here. So as you can see over here, for the value of f of x, for that polynomials that we talk about it, f of 0 was negative, and for this reason I just put it over here that f of 0 is less than 0. So f of 1 is positive and f of 1 is greater than 0 over here. As you can see, at the point 1, f of 1 is positive, the value of that one is positive, and f of 0 at this point is negative. You can see that this value is negative. You can calculate it easily by putting the 1 and 0 in the function. Since the function f is continuous and 0 is a middle point, that means that we have a roots between 0 and 1. So to restrict that roots, we should determine f of half. If I just determine f of half, then we can restrict our roots more and more. Means that if I calculate f of half at the point 0.5, so this is the 0.5, and as you can see again this value is negative, so f of half is negative. Right now we know that f of 1 is positive, so right now I can say that the roots should be a value between half and 1, and in this way we can restrict the roots more and more. We can determine the value between half and 1, means that 0.75. if you just find a midpoint between 1 and half, if you add them it's 1 and half, and divide it by 2 it will be 0.75. you can check the f of 0.75, then we will realize that for 0.75, if you substitute that value in a function, this f of 0.5 is positive. Right now this gonna be positive, and we know that f of half was negative, so right now we restrict ourselves to the roots between half and 0.75, and in this way we have a good approximation for a root of a function. And this is the method that we can restrict ourselves step by step and narrate the way to calculate the roots of function. So this is one of the application of IVT indeed for the continuous function. So let us take a look at one classic example of the continuous function. At the question, they ask you to determine the value of a and b such that the given function express the continuous functions. So as you can see, for this function that has three relations, for x less than 0 I have one relation, for x between 0 and 1 we have another relation, and for x greater than 1 also we have 5x squared minus 2x plus 3 as a condition for this function. So for this function they ask you to determine the value of a and b such that this function will be continuous. So to determine that one, we need to calculate the limit of this function at the left side of 0, right side of 0, left side of 1, and right side of 1. And all of these limits should be equal, means that the left side and right side limit of 0 should be equal to have a limit at that point. For the x tending to 1 also we have the same situation. If we calculate this limit and make it equal, then we have some condition for a and b, and then we can determine the value of a and b. So let us take a look at that example and try to solve it. First of all, let us calculate the limit of fx where x tending to 0 from left. Where we said that x tending to 0 from left means that x is less than 0. So we need to determine it by this equation. This equation should be substituted over here. Means that we have 3ax plus b should be replaced over here. So for the case that x tending to 0 from a right side, x should be greater than 0. So if x is greater than 0, then we should use this condition to calculate it. Means that we have 2b actually x squared minus 3x plus 1 minus 3x plus 1. We should substitute the value of a function by this condition. If x tending to 1 from left side means that x should be less than 1, and again we should use that condition to calculate the limit. Means that we should write 2b x squared minus 3x plus 1. We should substitute that one instead of f of x to calculate the limit. And for x greater than 1 or x tending to 1 from a right side, we should use the last condition, which is 5x squared minus 2x plus 3. Let me just put some b over here, a or b over here, to have a better function. 3b, let me just write it by 3b, and right now we have a better function over here, minus 5x squared minus 2x plus 3b. So right now if I want to calculate that the limits, you should simply substitute the value of x by the given things that you have it in each limits. At the first limit, instead of x I should put 0, so the remaining things will be b simply. At the right side, at the second limit, again if I just substitute x by 0, then all the terms except the last one, which is 1, is remained. So from the first and second one we realize that the value of b should be equal to 1. So it wasn't a bad idea to have more complicated things over here. Let me just change a bit a function and put a as well over here to have some condition like this over here. So we have b plus a then, and the result give us the b plus a as well. So I just modify the question a bit, and the first one will not give you directly the value of b. Indeed, it's said that b plus a will be equal to 1. So this is the first one. So at the second condition, you should substitute x by 1. So if I substitute it, then I have 2b minus 3 plus 1, which is minus 2. And at the last one, if I just put 1, then I have, let me just change again this value of b to a, to have some a as well in that equation as at the end. So 3a, and let us change that 1 as well to the a. So right now, if I substitute x by 1, then I have 5 minus 2, which is 3, 3 plus 3a. 3 plus 3a will be the result. So the right side and left side limits should be equal. So I have 2b minus 2, 2b minus 2 as a left side limit should be equal to the right side limit, which is 3 plus 3a. So right now I have two conditions. One of them is given at the first equation over here, and the another one is given here as a second relation that I have it. And I can write them in one system of the equation. Means that if I gathered both of these conditions, then I have a system of the equation. The first one said that b plus a should be equal to 1. b plus a should be equal to 1. And the second one said that if I shift that 3a to the left, then I have 2b minus 3a. 2b minus 3a is equal to 3 at the right side and 2 also shifted to the right, and I have 5 at the right. So right now, to solve this one, we need to solve that system of the equation. So it's only need to multiply the first equation by 3. Then I have the following things, means that I have 3b plus 3a equal to 1 and equal to 3 because I multiply all of them by 3. And the second one is 2b minus 3a equal to 5. You can solve the system of the equation with the different methods. So there are a lot of methods. I just solve it by the elimination methods, the Gauss elimination method. At the linear algebra courses, we have the detailed actually discussion about solving the system of the equation. Over here, after cancelling 3a and minus 3a, if I add these two equations, then I have 5b equal to 8. 5b equal to 8. And then you can calculate the value of b. The b will be equal to 8 over 5. And right now I can use the first equation to calculate a. And a will be equal to, from the first equation that I have it over here, a equal to 1 minus b. 1 minus b means that 1 minus 8 over 5. So 5 over 5, or 1 minus 8 over 5, will be minus 3 over 5. And we found the value of b and a such that the given function will be continuous. So after solving that example, it's not a bad idea to take a look at the different types of the discontinuity. So the first type of the discontinuity is as follows. So when at one point the function is discontinuous and it's a gap inside of that graph, then we can call that kind of the discontinuity as a removable discontinuity. In this case, the limit does exist. As you can see at the right side and left side, the limit does exist, but the value of a function is not defined at that point. To fill the gap and make the function continuous, it's only enough to define the value of a function at that given point as a limit of a function. So the right side limit over here, right hand limit, is defined as you can see over here by this definition, and the left hand as well. And if you consider that type of the function, you can define the function such that it's going to be continuous. So the main example is the example that we had it previously, sine x over x, which is not defined at x equal to 0. However, by defining the value of a function at that point as a 1, then the function will be continuous. So we can define it to make it function continuous. So we call that type of the discontinuity as a removable because we can remove that discontinuity. So it's only enough to define the value of a function at that point as a limit of a function at the given case. Another type of the discontinuity is a jump discontinuity, and as you can see over here, this jump discontinuity cannot be removed because over here the right side and left side limit are not equal. We cannot change the definition or the value of a function at that point such that the function will be continuous. However, we can define the right side continuity or left side continuity. If we fill the gap of a function with one of them, for instance, if I just give the value for the function at this point, then the function will be continuous from a right side. Or if I put the value of a function at the left by this value and fill the gap over here, then the function will be continuous at the left. But we cannot define the function such that it's going to be continuous. One of the type of this function is a sine function. If you consider the sine function as follow, indeed we just have a function that we denoted by sgn of x, which is the sine of x, then we can have the following definition for that sine of x, which is given by 1 for x as a positive, where x is positive is defined as 1, and if the x is negative, it's equal to -1. This sine function is a jump discontinuous function, and the given function has a simple graph. So if we consider the graph of this function, if we have this two-dimensional space, then you can see that for the positive value, the value of a function is 1. So we have this value at the positive side, and at the negative side we have a -1, and at the point 0, as you can see, it's open, means that we have this open circle at the 1 and -1 as well. So this sine function is important because we can reach to the absolute value function by using the sine function. Means that if I multiply the x by sine of x, if I multiply x by sine x, sine of x, then the result will be absolute value of x. Means that the result of this function, the multiplication of these two functions, will be absolute value of x, because if I multiply them, then I reach to this formula. It's equal to the x for the positive values, x for the positive values, and for the negative value we have minus x, and this will be the continuous function indeed. And it's a good example to see that the multiplication of one discontinuous function and one continuous function will be continuous as well. So the result will be the absolute value, and the shape of the absolute value function is known very well as a one function like this. I mean, the graph of this function, the absolute value, can be considered like this. If we consider it here, yes, we have minus x over here and plus x at the right side. So this is the shape of the absolute value of x as well. So the third type of the discontinuity is a case that we have the infinity at one point. For instance, this 1 over x function determined over here, and as you can see at the point 0 the value of function tends to infinity, and we cannot remove this discontinuity as well, where the x tending to 0, the value of the function tending to infinity. At the right side it's gonna be plus infinity because 1 is divided by 0 plus, and at the left side it's divided by 0 minus 1 over 0 minus, which determines the minus infinity, and this is the another type of the discontinuity. So the last type of the discontinuity that we have it over here is the ugly discontinuity. We call it the ugly because the oscillation of this function is too much around of the given point. For instance, one of the famous type of this discontinuity can be seen as a sine of 1 over x. I have the shape of this function that is created by the Desmos program, and as you can see, as much as you go inside and going closer to the point 0, it's too oscillated and it's an ugly discontinuity because you cannot see even that what's happened over there. As much as you go inside and inside of this function, as you can see, this discontinuity is too much and it's actually oscillated over here too much, and you cannot even calculate the value of that discontinuity. You can see that how it can be ugly when you take a look at the form of this function, and as much as you're gonna be closer to the point 0, that chaos or that type of the happening around of the point 0 is too difficult to be predicted over there. So by introducing this type of the discontinuity, the last type of this discontinuity, I finished this lecture at this point. But as I said it before, it's very difficult to determine or mention about the contents that we should cover in a calculus, since that every day the development in a science is coming out and we should reach to that point. Some of this concept will be added or removed from the concept of the calculus. We try to select the simplest part and the part that is covered with most of the course outline. However, some of this topics is not covered anymore, or some part is missed, but I try to just make the best choice of the topics for this course, and it totally depends on a university or on a teacher who teach this course to give you the concept or the topics that they need. It one of the biggest challenges in this course is covering all the topics clearly and give you the good and simple topics that can be helpful for your career. So thank you for attending this lecture. In the next lecture we will start the derivative, and we will discuss about different type of the derivative, and also we will talk about this type of the things. Thank you for attending, and we will see you in the next lecture. Thank you again.